Okay. All right, so section 2.1. All right, entitled frequency distributions and graphs. Okay. So in this section 2.1, we are going to learn how to organize our data into what is called a frequency distribution table. And once this data is organized into a distribution table, then we can construct various graphs from it. Here is a raw data set that consists of the ages of the 50 wealthiest people in the world. These are ages now. And so here are the ages. Now, order really doesn't mean anything in this data set the way they're arranged. But what we're going to do is we're going to take these 50 data points or 50 observations, and we're going to organize the data into what is called a frequency distribution table. Okay. Notice this order is not in any order of any kind, and it would be nice to know what the range of the data is. And the range of a data set is nothing more than the difference between the maximum and minimum value in a data set. Okay, so range. Now, there are 50 data points in this data set, which is quite a large data set, but in reality, there are data sets that are used every day that number in the hundreds of thousands or if not millions of data points. And in such a case there, you would probably want to sort your data using a computer system. Our TI-84 calculator can sort data. It's very easy to do so once you have your data into memory on your calculator. And so what I would like to do here is maybe show you how to sort data using your calculator here. Okay. So this is the TI-84 calculator, and we'll be using it quite a bit this semester. Now, I'm not going to type in those 50 observations, but I'm just going to show you in general how to sort a small data set. All right. And it would work for any size data set then. So the first thing you want to do is just turn your calculator on. And then you want to hit your stat button, STAT, which is right here. You hit your stat button. You have three menus: edit, calculate, and test menu. To enter data into memory, we're going to use our edit menu here, or edit command. And so we're going to hit the enter button with our cursor sitting on the edit. And then we're going to type in our data. We have lists here. I believe we have 6 lists at our disposal. Normally we have 6 lists at our disposal to enter in data. So this is kind of like a little mini spreadsheet, if you will. All right, so I'm just going to type in some data points here, and these data points are not going to be in any specific order. Okay, and I'm going to show you how to, now that I got this data entered into memory, after you type a data point, you hit the enter button, enter it in. You can scroll back through your list and take a quick look at it if you want. All right, now to sort this list is pretty simple. All we do is we get out of this mode by hitting second mode. Anytime you hit the second key followed by the mode button, it's the function in blue above the button that's activated. So the blue second key followed by a button activates the word in blue, which is quit. So it quits any application and takes me back to my home screen. All right, now to sort a list, there's different ways, but the most popular way is to hit your stat button. Go down to sort A or sort D. Sort A is designed to sort your list in ascending order from smallest to largest, top down. Sort D will sort a list in descending order, largest to smallest, top down. Let's sort our data in ascending order. So I will select the Sort A button, hit enter. And now we need to type in the name of the list that we wish to sort. Notice I put my data in list 1. Notice above the number 1 key in blue, I have L1 appearing. Above the number 2 key, I have L2 appearing. Above my number 3 key, I have L3 appearing in blue. Above the number 4 key, L4. L5 is above the number 5 key, and L6 is above the number 6 key. So I need to bring up the name list 1. So I hit my blue key followed by the number 1 key. That forces the name list 1 in for the argument of this function. Close it off with a closed parenthesis, then hit enter, and boom, your list has been sorted. To look at it, we go back to stat, stay on edit, hit enter, and you can see that list 1 has been sorted in ascending order. And it's that simple. Any questions how I sorted that list in ascending order? And again, you could have sorted it in descending order. It just depends what your preference is. All right. The nice
I have a question.
Yeah, go ahead.
It's not about the sort. I just noticed that I had the wrong calculator. It's TI 83 plus. Will that work, or it needs to be the 84?
Which one now? Which
I have TI 83 plus.
TI 83 plus? If you hit your stat button, do you see these menus here?
Yes. Oh wait, okay. It only gives me that when I hit the stat button, it gives me the options of. Sorry, I want to make sure that I just hit it. Oh yes, it gives me those options.
And if you hit your stat, if you go over to tests after hitting your stat button, do you see these tests?
Okay.
I think you should. The 83 and 84 are pretty much the same as far as the stats.
Yes, I see those.
All right. Your calculator will be okay. All right.
Okay, thank you.
All right. Anyways, any other questions about sorting? Okay. All right. So we're going to try to organize these 50 data points into a frequency distribution. And now a lot has been done here that we don't see happening behind the scenes. What they've constructed is called a frequency distribution table here. And frequency distributions have class limits, classes. And in the classes, they've indicated how many of the data points fall within the class limits of each class. For instance, in the first class, whose lower endpoint is 27 and upper endpoint is 35, there was one person in this age group that was among the wealthiest 50 people in the world. Notice that the most frequent age group of wealthy people is 54 to 62, containing 15 of the 50 observations. Okay, so this is called a frequency distribution table here. And how do they determine these classes? In other words, how many classes are going to use and the class limits to build this frequency distribution table? Well, we're going to learn how to do all this to actually build these classes here, okay? But they just basically said, okay, well, this is a frequency distribution table. We're going to use these classes, and then we're basically going to tally up as to how many data points fall in each class. Okay, so this is called a frequency distribution table. All right. Now, most frequency distribution tables have what are called class limits. All right, although some frequency distribution tables make use of what are called class boundaries. All right. The thing is with these class limits here is you would have to come up with a rule. Like if somebody is like 35 and a half years old, 35 years and 6 months old, you would have to come up with a rule or establish a rule that you employ consistently with all your data points and all your classes that would have you, determining in what class you would put that person as 35 and a half years old. You cannot put that person in both classes. That would be double counting a data point, which is one of the cardinal sins of statistics. And so maybe your rule says, well, anybody's age that is less than like 35.5 would go in this first class. But anybody's age that is 35 and a half up to 30, up to like 44.4 would go into the second class, okay, et cetera, et cetera. The key is whatever rule you establish for one class has to be the same for all of your classes and has to be applied equally to all your data points. As long as your rule, which might be different than somebody else's rule, is employed consistently, class to class to class, data point to data point to data point, your frequency distribution table is just as accurate as anybody else's, okay? But we'll see. Class limits help us to make a little easier determination as to what class to throw a data point in so as to not double count it. Notice another thing is that these classes do not overlap, and that's critical. I mean, if you had a class that ran from, let's say, ran from like 27 to like 37, and let's say your second class ran from 37 to, 36 to like 46, this would be a huge problem. Why would this be a problem? Well, because if I had a data point that was 36, the question is, what class are you going to throw it in? Do you agree that'd be a big problem here? Because we have overlap in our classes, we would be forced to double count 36, which is a no-no. So ladies and gentlemen, when you build a frequency distribution table, there cannot be any overlap between any classes. Another thing that is inherent with any accurate frequency distribution is that your class widths must be the same. With the exception of the first and the last classes where you could have open-ended classes, which are okay in certain cases. But in general, the width of these classes is determined by taking the difference between successive lower class limits or the difference between successive upper class limits. So how wide is this class here? That would be determined by taking 36 minus 27. Okay. So that would be the width of this class, or you could determine the width by taking the difference of 44 and 35. So whether you take the difference between the successive lower limits or upper limits, you'll get the same class width. And that must be true for all the classes. You must have the same width. If they don't have the same width, think about the problems you could encounter. If you had a class that went from 27 to 35, and let's say your next class went from 36 to like 55, ladies and gentlemen, which class is going to hog up more of your data points, the first or the second?
The second.
The second one will probably have more data points in it than the first one, 9 times out of 10, because it's just a wider class. And for that reason, that's going to lead us to an inaccurate understanding as to the dispersion of this data within the data set. So we got to make sure that our classes have the same width, all right? So basically put, there are 3 bases that you want to cover when you build a frequency distribution table. Number 1, all right, you don't want to ever have any overlap between classes. No overlap. Number 2, you want to make sure all your classes have the same width. And number 3, Usually you want to always make sure your smallest data point in your data set falls in the first class, and your largest data point in the data set falls in your last class. So those are three bases to make sure you have covered in designing a frequency distribution table. As long as your distribution table has those three requirements satisfied, your distribution table is just as accurate as anybody else's, right? There's a little bit of wiggle room as to the number of classes that you would use in your frequency distribution table. And although this PowerPoint presentation is not specifying how many classes to determine, I do have a formula which is used as a rule of thumb in statistics. And it goes like this: 2 raised to the k power must be greater than or equal to n being the number of data points in your data set. So k is equal to the number of classes that you would consider. N represents the number of data points in your data set, the number of observations you have in your data set here. Okay. So this is the number of data points here. This is a good inequality formula to use as a rule of thumb. It'll give you an idea as to like what you should consider for the total number of classes in a frequency distribution. For instance, there are there's 50 data points in this data set. And therefore, we would want to use bare minimum how many classes? Well, what integer do you have to raise? What integer power do you have to raise 2 to ensure that you have a value that's at least the size of 50? So 2 raised to what power here will ensure that you have at least 50? Well, 2 to the first power is 2. 2 to the second power is 4. 2 to the fourth power is 16. 2 to the fifth power is 32. 2 to the sixth power would be 64. All right, so it looks like if you raise 2 to about the sixth power, that will, suffice here for the number of classes that you could use here. Now, does that mean you have to use 6 classes? The answer is no. You have a little bit of leeway. Notice here they decided to use 8 classes. All right. But my point is you want to try to stay pretty close to round using about 6 classes. I would recommend that you use at least 6 classes. Okay. But you don't want to use too many classes. If you use too many classes, then you're defeating the purpose of what the frequency distribution table is all about. If you use too many classes, then what's going to happen is the frequency of each class the frequencies are going to approach a common value. And that's not going to be instructive at all in giving us a keen idea as to what the most commonly occurring data point in your data set is. So you want to adhere kind of close to this integer. You have to raise 2 to ensure that you get a value that is at least as large or larger than your size of your sample. Okay, so 6 classes would have worked here. You could use 7 classes, or they even used 8. I would not go above and beyond 8 classes, though. That's too many classes. Again, keep it close to 6. I would not want to use 5 classes. I would want to use 6, 7, or 8, somewhere in there. Okay. But again, so there is a little bit of latitude when you build these frequency distribution tables. Again, what I look for when you do build these things, and what Alex is going to look for, is that you don't have any overlap between your classes. All the classes have equal widths. And of little lesser importance, your smallest data point falls in your first class, largest data point falls in your last class. But you might want to jot this formula down, ladies and gentlemen, as it is not in this PowerPoint presentation. I don't see it anywhere, and I don't see it in your textbook either. So this inequality, hopefully you can just jot down somewhere. That's a rule of thumb as to how many classes to use in a frequency distribution. Okay. All right. Now, if the range of your numerical data is small, You could use each data value as its own class, which is, again, not really useful, though, for frequency distribution. Can you build frequency distributions for non-numeric data? And the answer is yes. If you have nominal or ordinal level data, you can still build a frequency distribution table. It's just that you're not going to have numeric class limits. You're going to have categorical labels, okay? All right, here's an example of a categorical non-numeric frequency distribution. 40 people were asked what they drink for breakfast. The choices were water, milk, juice, coffee, and tea. And notice these are the 40 responses. And we can build a frequency distribution table from this. The classes, of course, are non-numeric, and therefore you just have the labelings of the particular beverage as the classes. And then we would tally up how many people preferred each type of drink. Okay, of 40, 14 preferred water, 8 milk, 6 juice, 9 coffee, 3 tea. Your frequencies always have to add up to the sum of the total number of data points in your data set. If it doesn't, that's a big mistake. That means you either lost data or you fabricated data. And those are two no-nos in statistics. Right. We can also build a relative frequency distribution table by just finding the relative frequency of occurrence of each class by dividing the frequencies by the total. So if you take 14 and divide it by 40, you see that 35 hundredths of your observations fall in the first class. 8 divided by 40, 2/10 of your observations fall in the second class, et cetera, et cetera. You can turn these relative frequencies, which must sum up to 1, into percents just by multiplying them by 100%. And so you have a relative frequency distribution or a percentage distribution here. Okay, so any questions about these frequency distribution tables so far here? All right, now here is a frequency distribution for blood glucose levels in milligrams per deciliter of blood, I would imagine, for 50 randomly selected college students. Notice we do have our class limits over here, okay, for those particular milligram per deciliter readings. And then they also include another column, which is called class boundaries, okay? Class boundaries are nice in a way, ladies and gentlemen, because they help us to make it easier to determine in what class a data point would fall if it has like a tenth decimal attached to it. All right, it's easier to see or determine or come up with a rule as to what class to throw it into. In other words, if we have an observation that is 64.4, that's obviously going to go into first class. We have an observation that is 64.5, we just have to come up with a rule. And maybe our rule says this: if I have an observation at 64.5, I will throw it in the first class. Then if you establish that rule for that class, then if you have a data point that has an observation of 71.5, you must throw it in not the third class, but the second class. If your rule is this: if I have a data point that has a value of 64.5, I'll throw it in the second class. Then you must be consistent in applying that rule to other classes. For instance, if you have a data point that has an observational measurement of 71.5, you would have to throw it into the third class based on what you did with that previous data point. So again, as long as your rule is consistent, class to class to class, data point to data point to data point, you're okay. But if you're not consistent in your rule, applying it to classes and data points, then your frequency distribution is in error. Okay. Now, how do we establish these class boundaries? Well, class limits are integers. Class boundaries are always 0.5 away from the class limit. For instance, the lower class limit, okay, is 58. So the lower class boundary of class 1 will be 58 minus 5, or 57.5. The upper class boundary of the first class will be 64 plus 0.5, or 64.5. All right, so that's how you establish your class boundary values. either subtracting 0.5 or adding 0.5 to the lower or the upper class limit respectively. All right, notice your class widths would be the same. Whether you take 65 minus 58 or 71 minus 64, that will be equivalent. So look at to determine the widths of your classes here. Okay, the widths of your classes. Whether you take 65 minus 58 or take the difference between successive lower class limits, or take successive differences of upper class limits, or if you have class boundaries, ladies and gentlemen, it's just a matter of subtracting your lower class boundary from your upper class boundary to determine the width of the interval. In either case, all of these will generate the same accurate width for each class. Does that make sense, sir? 3 different ways of determining widths of classes. All right. Any questions about whether, what's the difference between class limits versus class boundaries and how to determine the width of a class, regardless of the method you use?
I'm sorry, can we go over boundary one more time?
Boundary values are always a half away from the class limit values. So the first class lower limit is 58. So the lower class boundary for the first class is going to be 58 minus 0.5, which is 57.5. The upper class limit for class 1 is 64. So the upper class boundary is going to be 64 plus a half, or 64.5. Okay.
Got it. Thank you.
That's how class boundaries are numbered. All right. All right.
Isn't there an overlap? So if you had like 64.5, would it go
Okay.
in?
Now again, that determines what rule you establish. Okay. If you have 64.5 for a data point in your data set, you have to come up with a rule. Suppose your rule, you could come up with a rule that says, okay, if it's 64.5, I'll throw it in the first class, but not the second class. Then you have to be consistent in applying that rule to all your other classes. For instance, if you had a data point that measured 78.5, what class are you going to throw it into? The third or the fourth? You throw it into the third class. Does that make sense? If your rule said, I'm going to throw 64.5 into the second class, then if you have a data point that is 78.5, you got to throw it into the what? The fourth class. As long as your rule is applied consistently. Does that make sense?
Yeah, thank you.
Okay. All right, this is just going over the class widths, how to determine the class widths. Oftentimes, ladies and gentlemen, we're going to have to construct we're going to have to come up with what are called class midpoints. And class midpoints can be determined one of 2 ways. If you're using boundaries, class boundaries, it's nothing more than the average of the lower and the upper class boundary values. So you just add the lower boundary value to the upper boundary value, divide by 2. That's the midpoint of that class. Or if you don't have boundaries, you just have class limits. If you take the average of the lower and the upper class limit of a class, you generate the midpoint for that class. That's how you generate midpoint values of a frequency distribution. Okay. So like, let's go back here, like for the first class, okay, what would be the midpoint of the first class here? Well, you could determine it one of 2 ways. You could take 58 plus what? 64 divided by 2. Okay, and what does that give you? Anybody got a calculator?
61.
61. Or you could determine the midpoint by taking the average of the lower and the upper class boundary. So 57.5 plus 64.5 divided by 2. And what do we get?
61 again.
61 again. Is that clear as to how we can generate midpoint values, whether we're using class limits or boundaries? Okay, either way. All right. So 61 would be the midpoint of the first class. And you would do that for all the other classes in computing their midpoints. Same thing. All right. This is basically just going over all the things that I talked about are important with a frequency distribution. Now they say there should be between 5 and 20 classes. Again, ladies and gentlemen, I would like you to use that formula 2 to the k power greater than or equal to the number of observations in your data set as a rule of thumb in general, okay? Because 5 to 20, that's a huge range here, all right? And that's not being specific enough as to like how many classes you should use for your data set. So this is a little bit too general here. I would like to use that inequality that I gave you. All right, now they prefer class widths to be odd, but you know, that's not a real critical thing. The reason why, if class widths are odd, then if you compute the midpoint of such a class that has odd widths, then your midpoints are going to come out with the same number of decimal places as your actual data values themselves do. But again, ladies and gentlemen, this is not a real critical situation here that you have odd widths for your classes. I mean, I've only seen that in this textbook. I've never seen that in any other textbook. So this will take as kind of like a grain of sand. All right, you could have even width classes. I mean, the midpoints are still going to work out okay, and et cetera, et cetera. That's not a real big deal there, all right? Now, the classes must be mutually exclusive. That's a way of saying that you cannot have any overlap between your classes. No overlap. That is important. That's critical. Classes must be continuous. Well, all numeric classes are continuous. That means it's a continual interval, correct? Which could contain an infinite number of decimals or fractional values. All right. The classes must be exhaustive. That means that you know, every data point in your data set has to fall in one of your classes. In other words, you cannot have a data point in your data set that does not find a place in one of your classes. That's no good. That's not inclusive enough for your distribution. So it has to, your classes have to exhaust all the possible values of your data set. Okay. So every data point must be found in a class. Classes must be equal in width. That's critical. All right. Now, as far as equal width is concerned, I have seen some frequency distributions where they relax this rule for the first and last classes, which are open-ended. Normally, our classes have equal widths. Okay, so this open-ended rule is not used too often. Once in a while, it is. For instance, if you had ages, you could say the last class consists of the age group that is 60 or older. All right. That's called an open-ended class, 60 or older. These other ones have specific limits. You see that there? Okay. So if you are ever going to use open-ended classes, they do occur with the first or the last class. But again, normally we don't do that. All right, in statistics. All right, now, how do we determine or how do we construct a frequency distribution table? Well, number one, we need to determine our classes. To determine our classes, how many classes we're going to use and the width of our classes, first we want to find the range of our data. That is to say, you take the maximum minus the minimum data value. Okay, so you need to determine the range of your data. And then, ladies, I mean, determine how many classes you're going to use. And again, as a ballpark idea, I would like you to choose at least k number of classes such that 2 raised to that power is at least as large as the number of observations in your data set. As a rule of thumb, choose at least k classes and don't go beyond too far beyond k classes. So if this is like comes up to be 6, you know, I would choose 6 classes or maybe 7. I'd kind of stay around there. Don't go choosing like 10 classes. Right? Find the width of each class. It's simply found by taking the range and dividing it by the number of classes. So when you have the range of your data, you'll take that number and you're going to divide it by the number of decided upon classes by using the aforementioned inequality. And that will give you the width of each class. Now, your widths, you want to round off to a nice whole number value. All right. Normally we round up. I mean, sometimes if you round down, that's not a big deal either. But normally we round up, but we like it to be equal to a nice whole number. You don't want to have class widths that have a decimal value. All right. That's extremely messy, and we always like to avoid that. So we want it to be a whole number. All right, select a starting point. Well, you need to determine what your lower class limit is going to be for your first class. All right. Once you establish the lower class limit of your first class, or the lower class boundary of your first class, then by using the width of your data set, you can then lay off all of your other classes until you exhaust the number of classes you decided upon, which is K classes. All right, find upper limits, find the boundaries. And then you want to basically tally up, okay, in which class each data point lies in. All right. And after you do that, you have your frequency distribution table. Now, oftentimes we like to also construct what's called a cumulative frequency distribution table, in which case the frequencies are basically added up as we go down and cut through the classes as we accumulate their values. You'll see that in an example. Okay. All right, so here's the 50 wealthiest ages of people in the world. The range of this data is 92 minus 27. That's the max minus min, which is 65. Now, 65, and that's the range of our data. And they're going to use 6 classes instead of 8. So what width would we use here? The width is going to be your range divided by 6, 65 divided by 6. And what is 65 divided by 6? That gives us like 10.833333. And so, ladies and gentlemen, we'd probably want to round the width up to what? Instead of using 10.8333 for a width, which we don't want to use, we'll round it up to maybe what? 11? Does that make sense for the width of each class? A nice whole number. All right, now how are we going to start these classes? Well, what was the minimum value in the data set? It was 27. You could start your lower class limit of class number 1 to be 27 itself. Could I use 26 for my lower limit of my first class, 26 instead of 27? The answer is yes. Could I use 28 as the lower class limit of my first class, 28? Would that work?
No.
No.
Not going to work, because 27 will not fall in any of our classes. And remember, our classes have to be what? Exhaustive. Okay. So you have to at least start your lower class limit off at some value a little less than 27. Now, you don't want to start it off at 20. That's too far away from 27. Maybe start it off at 27. Okay. All right. So we're going to start the lower class limit of the first class at 27. And the width is going to be 11. So what's 27 plus 11? That gives you 38. So 38 then will be the lower class limit of class 2. 38 plus 11 is 49. That'll be the lower class limit of class 3. 49 plus 11 is 60. That's the lower class limit of the 4th class, etc., etc. Then the upper class limit of the first class is going to go from 27 up to 37. The upper class limit of the second class will go up to 48, etc., etc., etc. Then the class boundaries, if you want to use these, remember, is always 0.5 taken away from the lower class limit or added on to the upper class limit. So these would be class boundaries. And again, if you have an observation that is like 37.5, you need to establish a rule that you're going to employ consistently for the rest of your data and your classes. As long as your rule is consistently applied, your rule is just as good as somebody else's, albeit they may decide a different rule than you. Okay. All right. Anyways, we tally up in which class each of these observations belong, and there you go. Okay. Does that make sense how we built this frequency distribution table here, deciding on 6 classes?
Yes.
See how, you see the thought process that goes into making sure you cover all the bases, okay, and you don't have any violations. All right. All right, now, ladies, I'm going to compute the cumulative frequencies. If we wanted to build a cumulative frequency distribution table, we would add another column. We would call it the cumulative frequency column. And it's very simple to do this. Basically, if you go from 0 up to 27, 0 up to 37, if you will, you've cut through the first class, and that only includes a frequency of 1. One observation falls in the first class. By the time you go all the way up to 48, you cut through the first 2 classes. That means to the frequency of 1 in the first class, you must add 10 more observations. And so now your cumulative frequency is up to 11 after you've cut through the first 2 classes. After you cut through the third class, you got to add, what, 13 more to 11? And you've accounted for 24 of your 50 data points in your data set. After you cut through the fourth class, you've accounted for 36 of your data points. And no surprise, as you cut through the last class, you've accounted for all 50 of your data points in the data set. Does this make sense how we're accumulating the frequencies as we cut through the classes? Make sense, sir? So that's called a cumulative frequency distribution table now, including this last column here. All right. Frequency distributions are, why even mess around with them? Well, they really organize our data. They organize it in a meaningful way, in the sense that we can tell very quickly, okay, what is the most common occurring data point in our data set, just by looking at your frequency distribution table. Not only does your frequency distribution table give you that information, but it also can give you basically the nature of your distribution as far as the variance that exists in your data set, what kind of spread you have about the mean of your data set. All right, we'll talk about that more in the future. You can also ascertain whether your data set is symmetric versus skewed, and if it's skewed, in what direction, positive or negative direction. The skewness or asymmetry of your data set will ultimately dictate what kind of analysis you'll throw at your data set, whether it would be a parametric test or maybe a non-parametric test. And so your frequency distribution table gives you a quick snapshot as to what your data is all about, as far as its shape is concerned, and as far as its distribution is concerned, data point to data point. So you can ascertain a lot of information from a frequency distribution a lot quicker than you could by sifting through raw data that's all mixed up. All right. Okay, any questions about that there? Okay, so let's see here. Normally I like to do some problems, but my fear is that I won't get through all my other PowerPoint presentations. I'd like to go through maybe the PowerPoint presentations first, which are short, and then go to the textbook and we can start working on some problems. That way, at least I covered all the material I need to cover. So that's what I'd like to do, to err on the side of caution. All right, section 2.2. We are going to learn how to represent data in frequency distributions graphically using what are called histograms, both frequency, relative, or cumulative frequency histograms, polygons, and ogive diagrams. So now we're going to learn how to build graphs. But in order to build a graph, ladies and gentlemen, first of all, you always have to have some sort of a table, because the graphs always are designed and basically constructed from the table. Okay, that's why we went through frequency distribution table first. All right, common statistical graphs would be like a histogram. It basically makes use of vertical bars. And these bars are used to determine the frequency of occurrence of any class of a data set. A frequency polygon is a line graph, okay, that makes use of midpoints of a class. And a cumulative frequency graph called an ogive, that's ogive, not ogive or ogive. It's ogive, is a cumulative frequency line graph that shows basically how our data points are accumulating as we cut through the classes of the distribution. Right now, in order to build these particular graphs, we always have an x-axis and a y-axis, a horizontal, vertical axis. On the x-axis, depending upon what kind of graph we're going to build, we're either going to have class limits or class boundaries, or we're going to have class midpoints. Okay, separating the tick marks. The vertical axis will indicate the frequency of each class in order to build a histogram, frequency polygon, or an ogive diagram. All right, here is an example of a frequency distribution, which basically includes data that represents record high temperatures for each of the 50 states. The class limits are not used to make this histogram. Instead, they used what? Class boundaries. Okay. So I have a question. What would be the width of these classes? Can anybody tell me the width of each of these classes? Well, the width is going to be the difference between the upper class boundary and the lower class boundary. And so it does appear that the width is going to be what?
5.
5. All these classes have a width of 5, right? Notice the two of the United States, 2 states had high record temperatures between 99 and a half degrees Fahrenheit and 104.5 degrees Fahrenheit. 18 of the 50 states had record high temperatures between 109.5 and 114.5 degrees. Once we build this frequency distribution table, we can then build a graph. And this is called a frequency histogram graph. Notice the horizontal axis contains the class boundaries. And the vertical axis contains the frequencies. Okay. So our first bar for class 1 goes 2 units high. The second bar goes 8 units high. The third bar, which represents the third class, goes 18 units high, etc., etc. Make sure you always label your axes. The horizontal axis is the temperature axis in degrees Fahrenheit, and the vertical axis is the frequency axis. And you can also give your graph a title, record high temperatures. Does that make sense how we build that frequency histogram there? Right? Frequency histogram. Okay. All right, now to build some of these other graphs, we're going to need the midpoints of each class. And to find the midpoint, you would just basically take the average of the lower and the upper class boundaries. So like the midpoint of 102 is obtained by taking 99.5 plus 104.5 and dividing that by 2. And that's how you crank out the midpoints of these classes. Notice the frequencies remain the same. So to build a frequency polygon, we populate the x-axis with not class boundaries, but with the class midpoints. Notice the class midpoints are laid out and they're evenly spaced on the x-axis. The vertical axis represents the frequency axis again. Horizontal axis is temperatures in degrees Fahrenheit. So notice 2 of our observations had a record high temperature of 102 degrees Fahrenheit. Okay, that's the midpoint. For 107 degrees, a midpoint high temperature value, we had 8 states that had that record high, etc., etc. here. This is called a frequency polygon here. Notice they connect the first dot with a dot that's on the what? The x-axis. And the last dot with a dot that's on the x-axis also. All right, you don't have to connect those. I've seen textbooks omit that. You don't have to have this first dot on the x-axis and the last dot on the x-axis. Line segments connecting the first and last data point. You don't need to really necessarily have those, but they just decided to put those in there. Okay, that's called a frequency polygon. That makes sense there, that graph?
Yes.
Okay. This is a cumulative frequency distribution table, and notice the observations accumulate as we cut through the classes. By the time we get through the last class, of course, we accounted for all of our data points. From this table, we can build an ogive diagram. Okay. And to build the ogive diagram, we basically change our class boundaries, ladies and gentlemen, into this. So for instance, how many observations basically fell from values that were less than 99.5? There were 0, none of them. How many observations were included that were less than 104.5? Well, that includes having cut through the first class. That's 2. How many observations had values less than 109.5? Well, that will have cut through the first 2 classes. So that will mean that we've encountered wait a minute here. Cumulative frequency. Okay, something don't seem right here. Less than 109.5 should be what? 10 plus 2, do you agree? That's not right. This should be what? That should
12.
be 12. Yeah, that should be 12. Less than 114.5 will have cut through the first 3 classes, which means we got to add an extra 28. So this should be up to what then?
40.
40.
41, do you agree? Less than 119.5. Wait a minute, wait, hold on a second. I'm sorry. These are not frequencies. These are cumulative frequencies. You don't accumulate cumulated frequencies. This is all not right. Sorry about that, ladies and gentlemen. These are correct. These are correct, and these are correct. All right. I thought these were frequencies or cumulative frequencies. Okay. So does this make sense here, this cumulative frequency distribution table? And you could represent it either this way using class boundaries, or you could represent it this way. All right. Either way, they're both the same. There's no difference in what they're showing. Okay. Now from either table, we can build an ogive diagram. And there would be your ogive diagram right here. Notice from 0 up to in less than 99.5, 0 observations are encountered. So you always want to start off with that first point that has this cumulative frequency of 0. You don't want to omit that. That's important to start that first point off at 99.5 at 0. And then by the time you get up to 104.5, you cut through the first class, which includes 2 observations, et cetera, et cetera. And by the time you cut through all classes, yes, you should be up here at 50, which accounts for all your data values. That's called a cumulative frequency graph or an ogive graph. Sometimes it's called a less than cumulative frequency graph, but we normally just call it an ogive graph. Does that make sense? Ogive graph. Okay. All right, relative frequency graphs or cumulative relative frequency graphs. All these involve is that you're going to have an extra column in your frequency distribution table. You're going to have either a relative frequency column, okay, or a relative cumulative frequency column, depending upon what graph you want to make. So here's the approximate net worth in thousands of dollars of 50 small businesses in a city. Okay, so 20 businesses had a net worth of between $49.5 thousand and $56.5 thousand, right, et cetera, et cetera. To compute the relative frequencies, we're going to take these frequencies and divide them by what? The total of all the frequencies. In other words, divide it by the size of the data set, which is 50. So how did they get this 0.16 here? they took what? 8 and divided it by 50. You agree? 8 divided by 50 is 0.16. 0.28 was obtained by taking 14 and dividing it by 50. 20 is obtained by taking 20. The relative frequency of the third class is obtained by taking 20 and dividing it by 50. So when you divide the frequencies by 50, all of them, you generate what are called relative frequencies. Okay, these are called relative frequencies. And these have to sum up to 1. Notice these are the midpoints of each class generated here. So when you generate the midpoints of each class and also the relative frequencies, then, ladies and gentlemen, you can build a this is let's see, 39.16. Yeah, this would be a relative frequency polygon, because notice the vertical axis is not just frequencies anymore, but relative frequencies. Notice the tick marks are evenly spaced by 500ths on the vertical axis. The horizontal axis consists of the midpoints of each class. So this is called a relative frequency polygon here. This would be a relative frequency what? Histogram, where they're using the class boundaries. So you can tell whether you got a histogram or a relative frequency histogram just by looking at the vertical axis and what the numbers are. These are relative frequencies, not just frequencies anymore. Okay. You can also build a relative cumulative frequency distribution, as you would accumulate the relative frequencies as you cut through the classes. And of course, obviously, by the time you cut through the last class, you've accounted for 100% of your data, or 1 as the cumulative relative frequency. From this table, you can then build a cumulative frequency graph. And there it would be. How do I know this is just not just an ordinary ogive? In other words, just a cumulative frequency graph. What tells me this is a cumulative relative frequency graph, or a relative relative ogive, if you will? Well, it's the vertical axis. The vertical axis, because those numbers are not frequencies; those are relative frequencies now, and they're actually cumulative relative frequencies. So that's a relative cumulative frequency graph, or a relative frequency ogive. All right, the shapes of your distributions. If you build frequency histograms for your data, the shape can be very instructive as to what type of data set you have. This first one, we say, is approximately a symmetric data set and approximately bell-shaped. Okay, it's approximately symmetric. In fact, yeah, it's not exactly symmetric, but it's approximately symmetric. If you draw a vertical dashed line right through the middle class here, and if you fold this graph about the vertical line, do you agree that this bar will match up perfectly with this bar? This bar will be pretty close to this bar, not exactly. That's why this is not perfectly symmetric. This bar looks like it'll match up perfectly in height with this bar, and this bar will match up perfectly with this bar here. So we call such a distribution symmetric or bell-shaped. Bell-shaped in the sense that if you connect the upper left or the upper right corners of these bars, you'll carve out a what? A bell shape. Everybody see that there? We'll discover that this distribution is extremely important when we get into probability, when we look at the normal probability distribution, which is bell-shaped like this. Okay. This distribution here, ladies and gentlemen, is called a uniform distribution, in the sense that the frequencies of each class are pretty much the same. That's called a uniform distribution. Uniform distributions are very, very close to forming a rectangular shape. Notice that. Pretty close to forming a rectangular shape. All right, these distributions are not bell-shaped, and I've never seen textbooks allude to them with these words, but this kind of looks like a J. You agree? This kind of looks like a big what? Big J also. We say these distributions are skewed, okay? They're not symmetric, they're not bell-shaped. We would say this distribution on the left is skewed to the left, in the sense that the class heights or values drop off more gradually to the right, to the left rather, of the highest occurring class. So the tail is longest to the left of the highest occurring class. For this distribution, the tail is longest to the right of the highest occurring class. So this distribution is skewed to the left. We say skewed left. And this distribution here is skewed to the right. Some textbooks say that the first distribution here is negatively skewed, and the first distribution is positively skewed. Okay. And this distribution to the left is also positively skewed, and the one to the left is negatively skewed. Because the tail of the histogram on the left, tail is longer to the right of the highest bar, and the tail is longest to the left of the highest bar on the graph to the right. So we say that's negatively skewed. Why positively and negatively skewed? You think of the number line, the x-axis. This direction is the positive direction. On the x-axis, this is the what? The negative direction. So this is positively skewed, this is negatively skewed. Questions about skewness or symmetry? All right. When we get into measures of descriptive statistics, you can tell where the mode of a data set is by looking at the highest bars. For instance, we would say that this data set has two modes. A mode would be occurring here and also here. These are the two highest bars. We would call this a bimodal data set because it appears to have two modes. A mode right here and a mode right here. Okay. This is bimodal. This is a graph that where the data set takes on like a U-shaped graph. This would not be bell-shaped. It appears to be symmetric, pretty symmetric about this vertical dashed line, but it is not bell-shaped. It's U-shaped. This data set appears to have, it looks like about two modes also, so it would also be bimodal. All right, if you had a bell-shaped data set that we've seen back here, this data set would have only one mode. And the mode would be right here. This would be unimodal, meaning one mode. Okay. The mode is the most frequently occurring data point in a data set. We'll go over that when we get into descriptive stats. All right. Now, ladies and gentlemen, how can we build like a frequency histogram using our calculator? Well, it's not too difficult to do. First, you enter your data into list one. Okay. And then you need to configure your x-axis, which has the appropriate range that your data exhibits here. It does not appear that this data is sorted in any way, shape, or form. So you definitely want to sort it to determine the range. And that will help you determine what minimum and maximum value you should use on your x-axis to make sure that you don't exclude any of your data points. I'll show you on a calculator how to build a frequency histogram. This is kind of walking you through it on this PowerPoint presentation here. Okay. All right. So what I don't like about this is the data sets are kind of large, but maybe we could do that. So, all right. Well, if you have your calculator, we can bring it up there. And we got to type all this data in here, though. So there'll be quite a bit of data entry, ladies and gentlemen, in this class here. Now I'm trying to figure out where to put this thing here. I don't know if we're going to be able to see this or not in its entirety here. Turn your calculator on, hit your stat button, go to edit. And then we got to type in your data here. We can see it. Okay. Now, it doesn't matter what order you type your data in. The key is you don't want to lose any data points. And you don't want to fabricate data either, okay? So with your data entry, ladies and gentlemen, you don't want to go too fast. You know, you want to just make sure that, you know, you are accurate. Okay, so I'm going to load up this list one with the raw data observations. Now, you see I have an error already because that should be 112 after 108. So again, just be careful. Or wait a minute. No, that should be 113. I had that correct. All right. So again, just be careful when you enter data in, because your analysis is at the mercy of the data you enter in. And I see that I got an error up here already. That should not be 17. That should be what? 117. Yeah. All right, 114, 110, 120, 120, 116, 115, 121, 117, 134. And obviously, my key stroking is a mess here. I didn't get that. Well, I'm having a hard time doing 117 for a second, for whatever reason. Really? Okay. 118, 18, 118, 113, 105, 118, 118, 113, 105, 118, 122, 117, 120, 110, 105. Hit the wrong button. Okay, so let's see. One oh five. 114, 118, 119, 118, 110, 114, 122, 111, 112, 109, 105, 106, 104, 114, 112, 109, 110, 111, and 114. Now, make sure that you have 50 observations. It appears that I do. Okay. All right. Now, you can sort this data if you want, determine the range. Sort in ascending order, you can do that. list number 1. And now the data has been sorted. So 100 is the smallest observation. And the largest observation would be would be 135 or 134. 134. So you want to go to window now, hit your window button at the top of your keyboard, and this enables you to configure your X and Y axis when you go to make your graph. Notice my X data ranges from, what was it, 100 to 134, I believe. So I'll have an X min value of 100, and my X max value is going to be at least 134. I'm going to type in 135. The spacing between my tick marks here, I'm just going to go with the spacing of like 5. The y-axis. Now, there's not going to be any such thing as negative frequencies on your y-axis, so you could just have like 0 here. And we got 50 observations. So like how many of these observations would fall in any class? What would be the maximum frequency for any class? Well, to err on the side of caution, I don't think you're going to have any more than 15 observations in each class. All right, and that would be good there. All right, so ladies and gentlemen, now to build a frequency histogram, once we have our data entered into our calculator and we also have our window configured appropriately. By the way, don't mess around with the resolution or delta X or the trace step. You don't have to mess with any of that. Hit second mode to quit. Clear your screen. You can go to your stat plot mode, which is accomplished by hitting your second button followed by the Y equal button. Notice above the Y equal button in blue are the words stat plot. Let's go into plot 1 by turning it on. Let's dive into it by hitting enter. Notice plot 1 is turned off. I'm going to toggle it on now with my cursor sitting on. I hit enter. It's now turned on. Hitting the right and down arrow key, we're going to navigate our blinking cursor till we have it sitting on the frequency histogram icon right there. Hit enter. And our data has been put into list 1, remember, okay? And now, ladies and gentlemen, we can build our frequency histogram. If you hit your zoom button and you go down to the zoom stat function, this is a marvelous function, zoom stat. What it does is it looks at your data behind the scenes very quickly. It determines the scale the range of your data, if you will. And it also looks at the window settings that you've established. And it's basically going to conform, construct your graph based on all this pertinent information that we entered into our machine. So if you just hit zoom stat, it basically takes care and graphs your stats graph, and that would be your histogram here. Notice if you hit your trace button at the top of your keyboard, there's a button that says trace. You can basically navigate from class to class by hitting your right or left arrow key. It gives you basically the minimum value of the class, the minimum class limit, the maximum class limit of the class, and determines how many observations fall in that class. So there were 18 observations that fell between 109 and about 114.6. Okay. So notice it looks like 1, 2, 3, 4, 5, 6, 7, 8 classes were used in building this frequency histogram here. So that's how you can build a quick frequency histogram using your calculator and using the raw data. Okay, that's raw data now. All right, and all the steps are there on this PowerPoint presentation if you forget any of those. They're there for your reviewing. Okay. Now, if you have group data, how would you, build a frequency histogram from group data. Well, what you would do in this case, ladies and gentlemen, where you actually have class boundaries or class limits, you would determine the midpoints of each class. And in list 1 of your calculator, you're going to put your class midpoints, and in list 2, you're going to populate list 2 with your frequencies. And then you can build your frequency histogram from that. You can also build a polygon graph and an ogive graph from that information too. So like if I bring up my calculator here, wait a minute here. If I bring up my calculator, okay, if I go to stat, edit. Now, how do you clear out data in a list? The quickest way to clear data out of a list is to just move your cursor up onto the name of the list and just hit your clear followed by your enter button. So clear, enter wipes away all the data in list 1. Now in list 1, I'm going to type in the midpoints, 102. 107. 112. Yeah, there's like a delay with the keystroking here and what's occurring on my PowerPoint. And it is pretty annoying. All right. Now in list 2, we're going to type in the midpoints of each class, the frequencies of each class. Now that you have the midpoints in list 1 and the frequencies in list 2, you can build a frequency histogram. So just go in your stat plot, second y equals. Turn plot 1 on, make sure it's configured for a frequency histogram. And select your X list, which is in list 1. And just hit zoom stat. And you get your two. Let me see something. What's going on here? Trace 102, 109. See, what's that? 117, 124. Something's wrong. Something's amiss.
Oh, we needed to put L2 in there to plot the frequencies. This is what it says in the book anyways.
Yeah, frequency is L2. Yeah, that's what it is. All right. Yeah, the frequency, because the frequency is like the weight of each class. The weight of each class is the frequency. So here's what we need to do here. And for the frequency, don't leave it as 1. Bring up list 2, because list 2 has the frequencies of each of these midpoints, which represent each class. That's what you need to type in. Okay. Now you hit zoom stat, and you should get your frequency histogram there. Okay, so that still appears to be a little off. A little off. I mean, it captures basically the essentials of the data, though, for the most part. Okay. All right, so let's see. We get the idea how to do that. Now, how would you make a frequency polygon here? Well, you bring your calculator up again with the midpoints in the first list and the frequencies in list 2. And to make a frequency polygon, you go back to stat plot, plot number 1. But this time you have to navigate your blinking cursor on the line graph. This is the line graph for a polygon graph right here. Make sure you select that icon. X list is list 1, Y list is list 2. This should be good to go now. Hit zoom. And then zoom stat, function number 9. You can scroll down to function number 9, hit enter, or you can just type in 9 to select that function quicker. Oh, that's a funky looking graph. What do I got going on here? Wow. There's something corrupt with my data or something? I have to go back to stat edit, take a look. Yeah, something's wrong with my data here. I don't know. Let's see.
Landon was saying that the fifth value in L1 was 112 and it should have been 122.
Oh my goodness. Yeah. 102, 107, 112, 117, and it should be 122. Oh, there you go. That should be one. Wait a minute here. That's the problem, obviously. So this should be 122. There we go. Okay. Now we hit graph, and there you go. And that's why my histogram was off too. I didn't have that data point correct there. See that? That looks a lot better, doesn't it? Matches theirs. All right, now an ogive graph. How do we do an ogive graph? Well, to do an ogive graph, we go back to our distribution table here. I don't even know what that is. What's going? I'm not sure what that was. All right, anyways. And for your ogive graph, ladies and gentlemen, what we would do is we're gonna have to go like this. So we're gonna have to go back to stat, edit. Now, remember, list 1 consists of what? Of the midpoints, correct? The class midpoints. We're gonna leave that alone there. But list 2 here, we're gonna have to clear out here. So list 2 is gonna contain we do want the midpoints on the ogive, right? I think so. Lower class boundary for the first group, two, L2, and L2 enter 0 for the first frequencies. Okay. All right. So what we're going to do here is we're not going to use the class midpoints for an ogive diagram. We're going to use the lower class boundaries here. So for this, we're going to have 99.5. Then we're going to have 1004.5, 109.5, 114.5, 119.5, 124.5, and 129.5. Okay. Now, in the second column here, we're going to have the cumulative frequencies. Up to 99.5, there are 0 observations in that first. Once you get up to 104.5, you cut through the first class, so that would have 2 observations. Once you get up to 109.5, you cut through the first 3 classes, so you're going to have, you have cut through the first 2 classes, so that'd be 2 plus 8 more, which is 10. 114.5 means you've cut through the first 3 classes, so you got to add what? 18 more. That'd be 28. Up to 119.5, you'll have cut through the first 4 classes, so that's going to be 28 plus 13 more. And that's going to be what? 41. 41 plus 7 more is up to 124.5. That'd be 48. And then once you get up to 129.5, you add one more. And okay, there should be one more here. Let's see. 129.5, and then this should be 49. Okay, and then the last one would be what? Up to 134.5. And that would be what, 50? Okay, 50. Okay, so now you can build an ogive diagram. Notice that these frequencies in list 2 are cumulative frequencies. And to build an ogive diagram, we are going to go back to stat plot, second y equals plot 1, and we're going to select line graph again. X list is list 1, and the y list is list 2. Zoom stat, and you now have an ogive diagram. You see that there? You hit your trace button, you can basically walk along, you know, these points here. Okay, ogive diagram. So that's how you can build the various diagrams on your calculator. And again, the good news is you have these slides to mull over at your own pace here, okay? I just wanted to show you how we can do a couple of those things there. All right. All right, there's just a couple of other graphs, ladies and gentlemen, in section 2.3, a bar graph, a Pareto graph, time series plot, pie graphs, and dot plots. You know, I don't see a stem and leaf plot. That's bizarre. Okay. All right, we've all seen bar graphs before. Bar graphs make use of bars. But the difference between a bar graph and a frequency histogram is that a frequency histogram has numeric class limits or class boundaries, whereas bar graphs do not. Bar graphs have just qualitative categorical labels, if you will, for each class. Okay. For instance, this bar graph to the left represents the first year college student spending in electronics, dorm decor, clothing, and shoes. And the bars, the length of the bar is proportional to the numeric value of spending. Okay. That's a horizontal bar graph. Vertical bar graph is to the right. You could build it as a vertical bar graph. Right. These are called bar graphs. They're not histograms. They're not frequency histograms because they don't have numeric class limits or numeric class boundaries. They're bar graphs. This is a compound bar graph. These are nice in comparing two different entities. This is comparing men to women as far as times that adults watch television for the various age groups. Okay. There you go. That's a dual bar graph. It enables you to compare the differences. A Pareto chart is a special type of bar graph. It's a bar graph in which the frequencies of the classes decrease strictly from left to right. So a Pareto graph or Pareto chart is a bar graph in which the heights of the bars decrease strictly from left to right. Okay, that's called a Pareto chart. And here's a Pareto chart for represents what? I don't know. Foods that are eaten. Okay. That's a Pareto chart. Again, it's a bar graph that just has order to it in the sense that the bars decrease in height from left to right strictly. Okay. Time series graph, any sort of time series plot or graph always has on the horizontal axis time, whether it be names of months of the year, hours, days, weeks, minutes, whatever the case might be, you have a time series plot. So you're always plotting something against time. And in this case, you're plotting the millions of cubic meters of something. Oh, the average water consumption in the city, million cubic meters for a 1 year period for the different months here. Okay, it's a time series plots. Time series plots are nice in that they can show you trends that data possess. All right, stock analysts use time series plots all the time to try to analyze trends, and they throw sophisticated trend analysis at them and use sophisticated mathematical models to try to model the trends based on past data as to try to make accurate predictions as to what a stock price is going to do in the near future. Okay, you can get into, you can cover a whole course in trend analysis. You can get into Box-Jenkins techniques for a moving average model. Okay, you can study that in a course in quantitative analysis. All right, but you can see that the trend is increasing and decreasing here. So time series plots give you a quick snapshot of the trends that exist in data. Here's a compound time series graph, which is basically enabling you to compare two different things. In this case, men and women versus the percent of what percent of men and women have been in the workforce for the different years. That's a dual time series plot. Pie graphs or circle graphs are round, as the name, as you would suspect, and the size of the slice of the pie is proportional to the numeric value of the category. All right, here is a data set, and this data set pertains to the pounds in millions of the various snacks that are consumed. Doesn't indicate what time period this is over. All right. But ladies and gentlemen, in order to determine the size of the slice of the pie that is allocated to each of these snacks here, all right, we're going to have to use the pounds and million numeric figure, and we're going to have to see what fraction of 360 degrees that affords us. 360 degrees, of course, being one complete circle. And so what we're going to do is we're going to take the frequency and divide it by the sum of all the frequencies, which in this case would be 30, with the understanding it's 30 million. And we'll multiply that by 100. That would turn that in. Actually, we're going to multiply that by 360 degrees. So like if you take 11.2 for the first class, if you will, potato chips, and divide that by 30, what's 11.2 divided by 30? Well, it's going to give you a decimal. When you multiply that by 360, that says that the first slice, which represents potato chips consumed, would have to have an angular measurement of 134.4 degrees of 360 degrees. That'll determine the size of that slice of the pie allocated for potato chips. 8.2 divided by 30 times 360 degrees will give you the size in degrees of the slice allocated for tortilla chips. Okay. So this is how they're computing the degree measure of each slice of the pie. If you do get a decimal value, of course, you want to round it off. All right. And of course, all these degree measures must sum up to 360 degrees. And to actually measure the size of these angles in here, like for potato chips, you'd actually use what's called a protractor. And you could measure out 134 degrees. And that would give you that size of that slice there. For popcorn, it was a 46-degree angle. This should only be a 46-degree angle measured on a protractor. Okay. This is what a protractor looks like here. We all see this here. This is called a protractor. Enables you to measure accurately degree measures, okay? So from here, all the way around is 180 degrees. Here to here is 90 degrees, et cetera, okay? So the protractor is used to build an accurate circle or pie graph in measuring out angles of each of these slices here. And you can see very quickly that potato chips was the most frequently consumed snack. The least consumed snack was what? Snack nuts. All right. You can even take these frequencies and divide them by the sum of all the frequencies, 30, and then multiply by 100% to determine what percentage of the entire area of the circle that each category consumes. So about 37.3% of all people surveyed opted for potato chips. Only 8.3% of all surveyed opted for snack nuts. Any questions how we build this circle graph or pie chart here? It's called a dot plot here. And basically a dot plot has just one axis, a horizontal axis. It's a number line that basically has tick marks evenly spaced. And the number of dots, the number of data points that have a specific numeric value are stacked just above the appropriate numeric value on the horizontal axis. For instance, how many observations had a value of 0 in here? This data set. Well, you count the number of dots stacked up on 0. 1, 2, 3, 4, 5, 6, 7, 8. 8 observations had a value of 0. Only 1 observation had a value of 13. There were no observations in our data set that had a value of 12. No observations had that had a value of 7, 8, or 9. This is called a dot plot. And you can tell very quickly that the most frequently occurring data point in the data set was 1. So dot plots also help to organize your information very quickly and give you a snapshot of the data in a very pleasing way, okay? Stem and leaf plots, ladies and gentlemen. Stem and leaf plots basically take your data set and dichotomize it into a stem portion versus a leaf portion. Now, what part do you call your stem and what part do you call your leaf portion? That depends on what kind of data you're working with. For instance, this data here, you can see that we have data that is in the ones digits, the tens digits, correct? And we have some data that's in the single digits, the tens, and the 20s, correct? So because of that, a nice choice for your stem portion of this data set is to use the tens digit. For single digit numbers, the tens digit is 0. For numbers that are in the tens, 1 is the tens digit. For numbers that are in the 20s, 2 is the tens digit. The leaf portion of the data set would be the ones digit of each observation. So this is the stem portion right here. This is the leaf portion right here. Okay. Now these stem and leaf plots have a very rigid order to them. It's always true as we go down the stem values, they must always increase strictly. As we go from left to right in the leaf values, they must increase strictly. So all stem and leaf plots have this characteristic. The stem values always increase top down. The leaf values always increase from left to right. So how many observations had a value of 1? Well, there's only one observation that had a value of 0, 1. How many observations had a value of 3? There's only one of them. How many observations had a value of 4? 0, 4 is 4. How many observations that measured 17 in our data set? There's 2 of them. 1, 7, that's 17, and 1, 7, that's 17. How many observations measured 24? 1, 24. Okay. How many observations had a measure of 19?
None.
None. Not one. Okay. This is called a stem and leaf plot. Does that make sense or that graph? Okay. Okay. All right, so let's see here. We don't have tons of time, but that covers at least the data I wanted to go over. All right, let's go to our textbook here quickly and see if we can do maybe a problem. We don't have much time left. Okay, so I'm going to go to section 2.1 in our textbook. Organizing data, all right. And I want to go down, scroll down to problem number 17 in our homework. Well, at least in the book here. Oh, I'm sorry. I want to start with 5 through 12. Let's go back up here. All right. Now, for these problems, it says find the class boundaries, midpoints, and widths of each class. Okay. So, ladies and gentlemen, for number 5, you can call this classwork number 1. If they give you a class that has a lower class limit of 58 and an upper class limit of 62, this will be classwork number 1. What would be the class boundaries of this class? What would be the midpoint of this class? And what would be the width of this class? Go ahead and do that. This is classwork number 1. This should not take too long. For number 5, determine the class boundaries, the midpoint, and the width.
And this classwork is what we have to email you before it's.
Yeah, you will hopefully email this to me by midnight tonight. Okay, classwork number 1. All right, so what would be the boundaries? Anybody? The boundaries.
It's 57.5 to like 62.5.
That's correct. What would be the midpoint?
I got 60.
60. Good. What would be the class width?
I got 5.
That's right. And you are correct. Okay. So those would be class boundaries, the midpoint value, and the width. All right, we good on that one? All right.
You want us to like take a picture of it and email it that to you, or how
Yeah,
would you
you
like?
can just do that. I don't care how you send it to me. Okay, just get it to me one way or another. All right. I don't care if it's a PNG file, PDF file, whatever it is, JPEG. All right. All right, problem number 9. Is this frequency distribution correct? Is this a correct, valid frequency distribution, or is there an error with it? Correct or invalid? Frequency distribution table, number 9.
It looks correct.
Well, it doesn't look like there's any overlap between the classes. What's the width of all the classes?
It doesn't, they're not all the same.
No good. The widths are not the same. 30 minus 20 is not the same thing as 35 minus 30. These classes do not have the same width. This is an invalid frequency distribution. No good. All right. So, ladies and gentlemen, add on to class work number 1, number 11. Is this a valid or invalid frequency distribution table? Number 11. This will be a part of next question for class work 1. Valid or invalid frequency distribution table?
Valid.
It's valid.
All right, so you're saying that's a valid
Yeah, it's valid.
frequency distribution table, correct? All right. So what's the class width?
2.
Is it 3?
It's not 2, it's 3. 165 minus 162 or 167 minus 164. 3. But what's 174 minus 168? Is that 3?
4.
174 minus 168, that's 6, isn't it?
Oh, my bad. Looking at the wrong one.
This is no
Yes.
good. Number 11 is no good because these classes don't have the same width, right? 174 minus 168 is not equal to 165 minus 162. These classes have unequal widths. That's invalid. And not only is that the case, but because we have such a gap here, in fact, I think they missed a class, didn't they? In between 168 and 174? I think they missed it.
That makes sense.
Yeah, the classes just don't have the same width.
Yeah.
bottom line. They don't have the same width, right? Okay. All right. Let's see. How about number 12, valid or invalid frequency distribution?
Invalid
not
because the
valid.
widths,
Invalid.
The widths are not the same for all the classes. 14 minus 9 is not the same thing as 26 minus 20. Again, unequal widths, okay? All right. Okay, now I have opened up some homework already, have I not? Chapter 1 on Alex. Has anybody started that homework or not?
I didn't start it, but it looks to be open.
Okay, so you are finding it, correct? It is there, all right. So that homework is available, ladies and gentlemen. And when is that homework due? Well, that'll be due by midnight, September, what, 16th? Do you agree? For chapter 1? And I'll be opening up homework for the sections that we went over today in the near future, all right? I'll let you know when it's open and available. Please try not to procrastinate on the homework. Don't get behind. Getting behind is going to make life miserable for this course. Try to stay up with it, okay? All right, I'll stay on the line for a couple minutes if there's any questions or concerns. So today we focused on various types of graphs that we can build from data sets. All right, we noticed that tables usually precede the graph. Okay, first you have to have some sort of a table before you build the graph. All right, ladies and gentlemen, take care. I'll be on the line for a couple minutes.
I had a question.